Okay, so ideally this should be more or less review from grade 10, but again, I didn't teach you grade 10, so I'm going to try to be as thorough as possible, but if at any point you're like, whoa, Chris, you're going too fast, slow me down. We're going to talk about energy in our last unit, and energy is another way of thinking about how the world works. Really, that's the whole goal of physics, right, is to understand motion of objects. We've talked about kinematics and dynamics for much of our year. If I were to ask you to talk to me about, like, what is kinematics about, you would probably say kinematics is about acceleration, distance, time, velocity initial, velocity final. That's really what kinematics is all about, the 5 variables. And those are things that really describe how things move. Right? If I ask you what is kinematics, it describes how are things going to move. If I throw this pen across the floor, we could measure how far it went, how long it took, how fast it moved. That's kinematics. Dynamics is about why is it moving? Why did it move in the first place? Well, because I threw it. I threw it by giving it a force. And that's really what dynamics is all about, is forces. Our middle unit on circular stuff really just talks about applying those same concepts to things going in circles. Okay? But energy is another way of approaching the question of why are things moving. Energy is another way of quantifying how and why things move. And you probably have some experience with energy. Hopefully you do. Because there's 2 main forms of energy we discuss. One is kinetic, one is potential. The best way that I can think of to describe kinetic energy is it's active energy. It's energy that is in a current active state. It is in motion. It is doing something right here, right now. Whereas potential energy, I don't know that I can think of a better word other than just the word itself, potential. Maybe you could use the word like future. Maybe that'd be a good word to use there. This is an energy that is currently happening. This is an energy that will happen eventually, just not yet. Okay. You guys have heard those words before? A good example of potential energy, a battery. Right? A battery has the potential to give you electricity. But if a battery is just sitting there on the counter, it's not doing anything yet. Right? If you then hook it up to some wires and let it run your, I don't know, pick a device, your radio, right? Then it's now in its active format. So those are the 2 different stages we have. And you should hopefully be somewhat familiar with these 2 formulas. So these are grade 10 formulas. I want to do about a 5-10 minute review just to make sure you're familiar with them. This is the formula for kinetic energy, which is basically stuff that's in motion. Right? If it is moving and it is in motion, we have kinetic energy. The formula is 1/2 mv squared. The other formula that, again, in theory, you should have learned in the past, but if not, I'm doing a recap right now, is one of the forms of potential energy is gravitational energy. There are many other forms of potential energy than just gravity, but if I were to have this pen and I hold it up here, does it have the potential to fall? Sure, as soon as I let it go, it will. Okay. Potential energy is based on 3 things: mass, gravity, and how high it is above the ground. A couple basic examples. Imagine that I had to drop a bowling ball on my foot. If I had to drop it from this high above the ground, like I'm talking like 3 centimeters above my foot, or way above the ground, which one's going to hurt more? Well, clearly the one where it falls further because it has more potential energy. But let's say that I wasn't dropping a bowling ball on my foot. Let's say I was dropping a tennis ball. Well, the difference there might be mass, right? If I drop something really light, it doesn't have that much energy. But if I drop it from really high, okay, now it has more energy. So there's really 2 variables: how heavy it is, its mass, and how high you drop it from above the ground. G in the middle is always 9.81 because we're on Earth. So hopefully those are familiar. Let's try some just basic examples. These come, like, for me, they come right out of my grade 10 notes. So hopefully this is familiar. Example 1. Let's say you have a shelf in your locker 1.8 meters above the floor and you put a textbook on it. Does your textbook have energy? Sure. It's not in motion, but could the textbook fall? Okay. Since it could fall, it has potential energy. And according to the formula mgh, we can calculate how much energy that textbook has. Maybe I should phrase it differently. We can calculate how much energy that textbook potentially has, because it's just sitting there right now, right? But if it were to fall, this is the energy it would have, right? So mass would be 1.2 kilograms. Gravity would be 9.81. And its height above the ground, 1.8. So times them together, 1.2 9.81, 1.8, 21. Does anyone remember the unit for energy by chance? Joules, yeah. It's a capital J for joule. Energy is measured in joules. It's named after James Joule, a famous scientist. You know, we always name them after scientists, right? Like Newtons and Watts. So it's joules. And with sig digs, I got 21 joules. Let's try another example. Car has a mass of 1,500 kilograms, moving at a speed of 100 kilometers an hour. Calculate its energy. Well, unless this car is flying, which would be cool, but it's probably not, it only has kinetic energy, right? It's not above the ground, it's on the ground. So in this example, we have just kinetic energy, which is 1/2 mv squared, which is 1/2 of 1,500 times by 100 squared, except I made a mistake on purpose. What did I do? Yeah, 100 kilometers an hour we need to convert. There was one of those on your test, by the way. If you forgot to convert a meters per second to a kilometers an hour, you're going to like facepalm and go, ah. So you divide by 3.6. So this number isn't actually 100, it's 27.7 repeating. I've done this twice today, I haven't memorized it by now. So you should actually take 0.5 times by 1,500 times by 27.7 repeating squared. And if you do that, you should get this number, 578,703 joules, which if you round it properly should be 5.79 times 10 to the 5 joules. Okay, let's talk about the scope of these two energies here. What would you rather have happen? Would you rather have a book fall off the top shelf of your locker and hit you on your foot? Or get hit by a car traveling at highway speeds? Which one has more energy? Thank you. Clearly the car, right? You know, so I mean, you can actually see the difference between this. The book falling would have 21 joules of energy. A car hitting you at highway speeds has like 500,000 joules of energy. Clearly there is a difference between the two, right? Well, okay, fair enough. What's the money to energy conversion? Okay. Does that make sense, though, why the scope of these numbers is so different? Is that the car has clearly more energy, right? So. Now, one of the other things we can do is we can combine them together. Okay? Energy values, just like any other values we've had, we can add them to each other. Here's a baseball that is moving, and it's above the ground. Not only is it moving, thereby implying kinetic energy, it's above the ground, thereby implying potential energy. So I'm just going to add them together. I'm going to find my potential energy. I'm going to add my kinetic energy, and that'll be my total energy. So potential energy is mass times gravity times height. Kinetic energy is 1/2 mv squared. Can I use the number 145? Kilograms, right? You got to convert to kilograms for physics. So this should be 0.145 and convert to kilograms, times by 9.81, times by 3.5 meters. And to that, I'm going to add 1/2 of 0.145, and the velocity was 18 squared. So you could do kinetic energy on its own. You could do potential energy on its own. You could add them together. All right. 0.145 times 981 times by 3.5 plus 0.5 times 145 times by 18 squared. If you do this right, you should get 28 joules. Hopefully, more or less, that's kind of review. I mean, it's maybe been a year or a year and a half since you've done grade 10 science, but it is directly out of the grade 10 curriculum. Is that fairly familiar? I'm seeing a lot of nodding people. Last question right here is something that is actually new. Let's say you have a slingshot. So imagine a slingshot, you pull back on the slingshot 6.8 centimeters, and the slingshot has a constant of 156. If you remember those constants, that means that's how stiff the material is that you're trying to pull back on. If I'm pulling back on a slingshot, what kind of energy is this? It's potential. Until I let go, right? But until that point, if I pull back on the slingshot, this is definitely potential energy. Once I let go, it's going to sling it back the other way and it'll become kinetic. But we're going to talk about that when we do conservation of energy later. So this shouldn't be familiar to you, I'm guessing, unless you had a teacher who really went above and beyond. So I do have a new formula I have to show you. Formula is pretty straightforward. It is an alternate formula for potential energy, but you may only use it if it's a spring. So it's 1/2 of kx squared, which is kind of cool because it's the kinetic energy formula, right? You know how it was 1/2 mv squared? It's just k is how stiff your spring is, and x is how far back you pull on it. So using the values from the previous page, k I believe was 156, x was 6.8. However, it was 6.8 centimeters, so I've got to convert it and make it like 0.068. So it's pretty straightforward. If I do 1/2 of 156 by 0.068, I end up getting this much energy for anyone who's following along and trying it. So quick recap. Ideally, you've already learned at some point about kinetic versus potential energies. You probably know the gravitational energy formula and the kinetic formula. Here's a new one. For the most part, you just plug numbers in. And sometimes you have to add energies to each other. Like, for example, what if I had a slingshot that was above the ground? I could use this formula here to calculate how much energy you have just due to the slingshot part. And then I could add a mass, gravity, height if you were shooting a slingshot off the roof of your house. So you could just combine them together. So far, so good? No one's vigorously shaking their head. No, we're moving on. Okay, another thing that ideally you might have learned a bit about in the past is what's known as work. I'm going to talk about the work energy theorem in a second, but first I want to discuss what work is. But before I discuss what work is, its definition actually comes from energy. The technical definition of energy in physics is the ability to do work. If you do a task, you do it because you had energy. Energy allows you to do a task. So work, in a way, is like a task. But in the definition of work, we're more specific. Work as a task always involves two things: a force causing motion over a distance. Those are the two things. There has to be a force of some kind. There has to be a distance moved of some kind, and that's work. And you probably learned this formula last year at some point. Work is equal to force times distance. Does that sound familiar, maybe? And that's a valid formula. We're going to work with that again in a bit. But what I want to talk about, which may be new, I'm not sure whether it is or not, but is how these two things are linked. Okay. One of the theories, you know there's those physics principles on your data sheet? If you have a data sheet nearby. Physics principle 0 is uniform motion. 1 is accelerated motion. 2 is uniform accelerated circular motion. 3 is the work energy theorem. What it basically states is that energy lets you do work. Or work comes because you used your energy. Okay? That's the work energy theorem, is that these two things are interrelated. Let me say that one more time. Energy lets you do work. Work comes because you have energy. Right? Even just think of like work as your job. When you go to your job and go do whatever work is in that context, you need energy to do that work. If you didn't go to sleep the night beforehand, if you didn't eat food, you wouldn't have the energy you need to do work. So they're the same thing as each other. Work gives you energy, energy happens, no. Work comes from energy, energy lets you do work. Maybe a silly analogy, but you guys ever play the video game The Sims? Or games like that where you have like a health bar or like an energy bar? Or like honestly any video game in which there's like, I don't know, like you have life, if that makes sense. And as you slowly lose your life, you're slowly dying, right? As you use up your energy, you're doing tasks, right? And so if you work really, really hard, your energy meter goes down quickly, right? If you're just resting around doing nothing, your energy meter doesn't really go down as far, right? That's what the work energy theorem is. Work and energy are related to each other. Okay, I'm going to come back to that in a bit, because now I want to spend a few more minutes talking about what work is, though. I told you that work is based on energy, but work, from a physics point of view, has to require a force and a distance. Has to, okay? Because an object actually has to move. Based on this, if I were to ask you how much work is done if you're just sitting in your desk writing a test, the answer is you didn't do any. from a physics point of view. Why not? Because you have to move. Now, you might argue, well, you moved your hands around a little bit, but it has to be through a displacement. Displacement would imply that like you actually have to go from point A to point B, right? Like if I move my hand up to here and back again, I really haven't moved at all, right? If I were to wave my hands around like crazy, but I'm back to where I started, I didn't actually undergo a displacement. A displacement means you actually have to change your location. So if you're sitting in your desk writing a test, technically you're not actually doing any work from a physics point of view, because objects actually have to move. Does that make sense? A second little thing I want to talk about for work is this second example here. Imagine there's a student walking down the hallway with a backpack full of physics homework. So here's a person, there's a backpack on their back, and it's just packed full of all those physics assignments you're going to do, right? Yeah. Let's talk about a free body diagram of this object right here. The most powerful force in this scenario is probably the force of gravity, because the force of gravity is pulling all of these books down. But if this person walks down the hallway in this direction right here, technically no work is done. Now, I'm not sure they've ever seen this before, but in order for work to be done, the force of gravity and the distance have to be in the same direction. If the force of gravity is pulling you downwards, but you just happen to be walking in this direction right here, that doesn't count either. Force and distance have to be in the same plane of motion, which means that chances are your grade 10 teacher kind of lied to you a little bit when they gave you this formula here, because this is not actually the formula for work. And if you look on your formula sheet that I would have given you, the formula for work is actually this one right here. It's work equals force times distance, cos theta. And what you're probably non-familiar with is this cosine theta part, probably, because I'm guessing your teacher just didn't deal with the cosine of theta. Here's the rationale as to why. We can now explain it better using vectors. Imagine there's a box right here, and you're now pulling with a force, like there's a rope and you're pulling kind of on an angle right here. Well, if the box slides along the ground in this direction like this, the force that you used right here, we only get to count the x portion of the force. You know how there's the y and x components of a vector? Well, if the distance is going in the x direction, we only are allowed to count the x component of your force. So like just to pretend, make up some numbers, imagine that this force right here was 10 newtons on the hypotenuse. I'm not going to give you an angle, but just for like pretend's sake, maybe this is actually 8 newtons, and this side over here is 7 newtons, just as like a pretend example for a triangle. When I use the formula force times distance, I can't just use this 10 newtons right here, because some of that 10 newtons is pulling up, and some of it's pulling over, and I'm only allowed to count the component that's in the same direction as my motion. And so that's why there's cosine attached right here. The reason why it's cosine is adjacent over hypotenuse, and this side right here is your adjacent. So that's why there's this little tag on the end here. Now, in this example right here, clearly this is being pulled with a bit of an angle upwards, but let's say you had a box, and let's say that you just did pull it in a straight line. What angle would you use if you were just pulling directly flat? 0, yeah, right? Because this would be like, say, 2 degrees, and this would be 10 degrees, and this would be 45 degrees. But if you pulled it exactly flat, it means that your angle is actually 0. Now, the reason why in grade 10 we probably didn't show you the little cosine part of this is because to make things simple, we always made it flat, probably, like it was always along flat ground. And if the angle is 0, if any of you have a calculator, take cosine and do cosine of 0. Cosine of 0 should be 1 if you're in degrees, which basically means that all of this is equal to number 1, which is why teachers usually skip showing that to you when you first learn about it. But now that we've talked more about vectors, we can't skip the cosine theta part. So it's pretty straightforward. You type in your force, you type in your distance, but if there's an angle, you just have to account for it, that's all. So let's try some examples. Example 1. I don't even have numbers on here, I just have this as just kind of like a reference. Here's a box. Let's say that you pulled with a force of 10 newtons, and let's say that it went 10 meters, just as nice, easy numbers. If this was you back in grade 10, you might think, oh, okay, the amount of work you do is force times distance. So you might think you go 10 by 10. Technically, that's not quite correct, because although you are pulling kind of to the side at 10 newtons, we can only count the x portion right here. And as a fast way of knowing what the x portion should be, it's always cosine, right? The opposite side right here would involve sine. The adjacent side involves cosine. So you do force times distance times cosine of theta. So you have to times by the cosine of 30 in this example. That's all. So the amount of work you do is just slightly different. That's all. 10 by 10 by cosine 30 gives me 87. That's my answer. Okay, a couple of thoughts here. We need to know the unit for work. I haven't talked about that, I think, yet. The standard unit for work, force is measured in newtons. Distance is measured in meters. So it's a really awkward unit. We often call it a Newton meter, an NM, a Newton meter. However, we often don't leave our unit of work in Newton meters. We often convert it to joules. And the reason why we're allowed to do that is through the work energy theorem. If you did 87 Newton meters worth of work, it came at the cost of 87 joules of energy. Can I phrase that again? If you were able to do 87 Newton meters worth of work, how were you able to do that work? It came because you used 87 joules of energy. So although we can write our units in Newton meters, we often put work in joules. Technically, energy is supposed to be in joules. But since work is energy, we can kind of like cheat a little bit here. Because joules is a lot easier than Newton meters. That makes sense? Okay, moving on. Next example, say you've got a force of 8.1 newtons used to pull a 60 kilogram object along the ground over a distance of 2.3 meters. Find your work done. You may find it helpful just to draw a rough picture here. So here's flat ground. Yeah, that was flat ground. What forces are involved in a box? Well, force of gravity, pulling it down. Normal force keeps it from crashing to the ground. Could be friction. Yeah, why don't we say that there could be some friction pulling back on us, but it looks like we are being pulled by an applied force, and the applied force was 8.1 newtons. Okay. Now, just based on the applied force, I know that friction could be slowing you down, and we could try to account for that later, but I don't really need to here. The work being done is based on the work of my applied force. So even though friction will slow me down, and I won't go as fast, I still traveled 2.3 meters. So my formula is still the same as it always was. Work is force times distance times the cosine of any angle required. The force that I was using is 8.1 newtons. I don't know what friction was slowing me down on, but that doesn't matter, right? The work that I was doing to pull the box is still 8.1. The distance that I pulled it over was 2.3 meters. And cosine of theta, it didn't really give me an angle, so I'm going to assume it's cosine of 0 and just skip that whole bit. Let's say that there is a force of friction. The force of friction is just going to make it so that I'm slowed down. I'm still going 2.3 meters. If there's friction, it means I get there slower. That's all, right? Like the more friction there is, the longer it will take for me to travel the 2.3 meters. But the work that I'm doing is based on the effort that I'm putting in. So even if there was a force of friction of 2.3 newtons, I wouldn't even use it anyways. It really isn't relevant to this question. So, okay, anyways, finishing this off, 8.1 would times by 2.3 to give me with 2 sig digs 19 joules of 19 joules of work based on 19 joules of energy. Sound good? Okay, one last example, then we're almost done. As you look through this question here, you can probably kind of see, oh, this time I gave you an angle, right? So I'm not even going to draw the free body diagram. Work is based on my force. I pulled 76 newtons over a distance of 12.7 meters. However, in this example here, I pulled this box. The box went that direction, but I pulled it a bit of an angle, so I have to account for the angle this time and just include the cosine of 35. That's all. So I'm kind of blitzing through this last one. Hopefully that's okay. 76 times 12.7. This time use cosine 35. If you do this, you end up getting 790.64. I want to do two things simultaneously here. One, that's work. but work is from energy, right? Work happens because of energy. So really, my energy is the same number here, which means it's in joules. And now if I want to do sig digs, the 35 degrees limits me to 2 sig digs. So it'd be 7.9 times 10 to the 2 joules. That's how much energy you used to pull the box. So energy used, 790. Work done, 790. That's the work energy theorem. Of all of the things on your data sheet that we learn about for physics principles, work energy theorem has got to be the easiest one, because literally whatever you have for work is energy done. So, sound good? Last thoughts. Just like with previous units, there are some graphs that we can do. And I want to do a kind of a quick recap of some graphing stuff we've learned previously before I come back to this. In one of our earliest units, we learned the formula velocity is equal to distance over time. That's like your very basic, like the first formula you learn in physics, right? V is d over t. What we've then learned then is that if you plot d over t on a graph and you get yourself a nice slope to it, the slope of this graph is d over t. And since d over t is your velocity, your slope is your speed. You guys remember doing that from way back when? Another graph we learned about is if you were to ever plot velocity and time, because there's a formula that says acceleration is velocity over time. So again, with that same logic, if you then find the slope of a graph, the slope of this graph would be v over t, but since v over t is acceleration, your slope is acceleration. One of the other things we learned, and we haven't done this since like February, but do you guys remember having to find areas of shapes from a while back? Right? And the way that worked was a little bit different. If you take the formula v equals d over t, but you rearrange it and take time and swing it up to the other side and go velocity times time is equal distance, this is kind of like how area is equal to length times width. If you consider this to be a length and this to be a width, if you find the area of this shape, it's what happens when you multiply these two numbers by each other. So velocity times time is actually a distance. And we did some questions where I gave you like a graph that looked, I think, kind of like this. And then you were supposed to find like the area of different shapes, you know. So if you find this area, this area, this area, and this area, if you add them all up, it was the distance. Okay. That same logic then can be applied to this current unit. So let's go back to this. We've learned the formula work is force times distance. Now, assuming that they're in the same direction of motion, so we can ignore the cosine part of it, what that means then is that if you plot a graph of force next to a graph of distance or displacement, if you were to then find the area of any shapes, the area of those shapes would be your work. That's all. Slope means nothing, by the way. If you were to take force and divide by distance and find that slope, there is no formula where force divided by distance really matters to us, but force times distance is. So one of the things I need to summarize here is that if you ever divide two numbers, it's equal to a slope. And if you ever multiply two numbers, it's equal to an area. If what they multiply is purposeful, you could find out how much work was done or how much energy was used. So I've got one last example, then I'm done. Here's an example. I found this graph online. It is force over displacement. And I asked you how much work was done. I could just as easily ask you how much energy was used, because it's kind of the same thing, isn't it? Work done is energy used. So if I were to ask you how much energy had to be used in this graph right here, you would just use area. Because the way it works is that work is equal to force times distance. And that's really your area being equal to like a length times a width. So the only difference here is that we have to use like a triangle on this one. Doesn't this make sense though? If you do no force, you get no motion. Doesn't that seem logical? Newton's first law. If it's not moving, unless you push it, it's not going to move. So if you use 0 newtons of force, it won't move, right? Whereas if you use, say, like 110 meters, it happened because there was 160,000 newtons of force, right? Your formula for area will be 1/2, because it's a triangle, right? 1/2 base height. 1/2 of 110 by 160,000. That would be your area. your area would be equal to work, but work is energy. So that's all you need to know. If I give you a graph then, and I ask you to find energy or work, find the area underneath it. Sound good? And that's it. All right, do the same thing, just humor me. On a scale of 1 to 10, 1 being you didn't know any of this, 10 being you knew this already from a previous class, where would you rank yourself? Yeah, most kids earlier gave me about a 9. Is that pretty fair? Yeah, somewhere reasonably high. I would suggest that things that I didn't expect you to know, but again, it depends on your teacher. I don't know whether you knew about the graph, and I'm not sure you knew about the spring slingshot formula, and maybe you knew about the angle in the work distance formula, but other than that, most of it ideally should have been review. So like as a quick 30-second recap, here's 3 things you should have learned today. 1, you should have relearned your formulas for energy. 1/2 mv squared, mgh, and 1/2 kx squared. Those 3 formulas. They're pretty straightforward. Second thing is we talked a bit about the work energy theorem. Work lets you do energy, and no, energy lets you do work, and work comes because you use your energy. They're the same as each other. The third thing is this graphing concept. As long as you understand how to find area of triangles and rectangles, it's pretty easy. You just need to remember what to do. So, and that's my lesson. Okay, quick recap, and then if you'd like to, you guys are welcome to leave. If you'd like to look at your unit tests, though, I have them out. But let me just do a quick recap of next week. You're not here Monday, unless you're here for leadership stuff, so enjoy Monday. I am making a YouTube video on conservation laws, which we're going to watch Wednesday. I'm going to try to make it either tonight or tomorrow night. So if you check my website on Monday, if you want to get ahead of the game, feel free to watch the Wednesday lesson on Monday when you have a day off of school. Tuesday, when we talk about systems, the notes are literally like 5 to 10 minutes tops. It is a very short lesson. So on Tuesday, I would really like to go through your unit tests as a whole class. I want to analyze them, figure out what it is that you made mistakes on. Because if you're like at all like the previous 2 classes, when a few of them looked it over, they've had a lot of like, which is fine. It is fine. You are still in the learning stage. It is okay to make mistakes. Please don't ever let someone tell you not to make mistakes. Look, Albert Einstein said, anyone who's never made a mistake has never tried anything new. So in my class, it is safe to make mistakes. You're allowed to. I want you to, in fact. So that'll be Tuesday, Wednesday. Thursday's a work day. Friday, we're going to do our last lesson on power. And that is it. We are then done curriculum as of May 31st, which is awesome. So, okay, that's all I needed to cover. Anybody have any questions? Okay. Guys, you're free to go if you want, or if you'd like to look at your unit test for a little bit, I've got them here. So why don't I stop the video, and then if you want to see them, you can take a look.